Good morning, team. Chemistry coach coming at you. You're probably getting real sick of hearing that, but I get a lot of emails from students and stuff that are, maybe it's late at night, 2 in the morning or something, or maybe you got a real cool job, perfect job for college where you could like study while you're working, right? You have something where you could do that. I wasn't able to do that. I paid my way through college working at a semiconductor plant. So I had to wear those so I'd go in and like 10 at night or whatever, and I'd work till 2 or 3 in the morning, part-time throughout the week, and then full-time on Saturdays and Sundays throughout the summers to pay my way through college. But I'd have to go in these fabs with this big, those big bunny suits with the goggles, and you only get to know people by their eyes and their voices, right? And then, maybe you'd walk through the lunchroom and they'd be out of their bunny suit, and you're like, that's what you look like. Whoa. I would have never guessed it. It was kind of fun. It was a neat experience, learning how to make, working with semiconductors and making transistors and whatnot. Crazy times. Well, I went off on a tangent immediately there. I don't know where I was going with that. Anyway, we're going to be looking at solid. Woo, down the bunny trail we go. Hop, 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 hop. Right? Amazing I ever got through, 10 plus years of college. My focus, I'd be in lecture and I'd be like 5 minutes into it. I'd be like, whoa, and I'd be gone. All right, so solid properties. We're going to keep it simple. We're just going to look at melting and sublimation. Okay, we already looked at, evaporation and boiling and whatnot. So let's start with melting. A lot of review here. Melting and of course the heat of fusion or molar heat of fusion, depending on your units. I highly recommend you go back to our lectures on thermal chemistry from first semester of general chemistry. And I made a video just on heat. So it talks about, when you add thermal energy or heat to something and if there's no phase change and you're increasing the particle vibrations and rotations, that increased atomic or molecular motion increases the temperature. So the Q equals ms delta T, remember that? So you can calculate the amount of energy it takes to raise the temperature of a certain substance a certain number of degrees, et cetera, et cetera. I'd review that. But specifically the one on phase changes, because that's what we're focused on now. So remember the Q equals N delta H. N is the number of moles. Delta H would be the molar enthalpy of that phase change, molar heat of vaporization, molar heat of fusion, right? So what we're going to look at now is, can we rank those? Can we kind of estimate if that would be high or low, and how would that impact melting points and solid properties? So great video to review. It's going to help a lot. So again, melting, or what they call fusion. I just call it melting. Why do you have to call it fusion? Okay. That's obviously the phase change from a solid to a liquid, right? Converting that. And during that, the temperature's not changing. So when you're heating a substance up and increasing the motions, that's Q equals ms delta T. But once you get to that phase change at the melting points or boiling points, whatever it is, there's no longer an increase in temperature. This is all reviewed from that video there, because all that energy is going into disrupting the intermolecular forces. Now, when you're converting from a liquid to a gas, you're breaking those intermolecular forces. When you're going from a solid to a liquid, you're disrupting them, right? So you're going from a solid, and then you heat it up enough, and it's increasing in temperature, and then when you get to the phase change, it goes and now they're a little more mobile, and that's why liquids can, they don't expand, right, like a gas does, but they can conform to the shape of their container. They don't have a definitive shape like a solid would, but they tend to have a definitive volume. So that's fusion. And then the reverse process of that, right, where you're starting with a liquid and you're cooling it down, so it's vibrating, rotating, doing all this stuff, and you're cooling it down, and you lock those intermolecular forces into place, and it has a rigid shape, rigid volume. So that's freezing or solidification, not precipitation. Precipitation is when you have ionic solutions, right? You have cations and anions moving around in two solutions. You mix them, rearranges those ions, and then they can, maybe the cation from one solution reacts with the anion from the other and forms a solid. That's precipitation. We're talking about solidification or freezing, which is just a phase change. It is the same substance. It's a physical change from the liquid state to the solid state. Right, just get it cold enough, and boom, those intermolecular forces lock into place. So just to review there, so let's look at melting points and molar heats of fusion. Now, we're always going to do, at least in my class, the units of kilojoules per mole. That's why we call it molar heat of fusion. But if you do kilojoules per gram, you just call it like the enthalpy of fusion or heat of fusion. So again, enthalpy or heat used interchangeably there. Let's look at those. All right, let's look at the two main properties of solids we're looking at as according to these phase changes, right? Melting point and molar heat of fusion. That's really going to be the impactful numbers for us. You don't have to memorize any of those other than water. I would expect you to know the melting and freezing points of water, boiling point, well, which is the same thing, boiling points of water, yada, yada. You'll probably memorize the molar heat of vaporization and fusion for water because you use them a lot, but I'll always provide you those values. All right, so again, these phase changes, whether you have melting or fusion, solid to liquid, or freezing / solidification, liquid to solid, those occur at a specific temperature. Now, I'm not going to put it down. Now, when we looked at the last video with the Clausius-Clapeyron equation, we found that with vapor pressure curves, the boiling point's quite dependent on external pressure, isn't it? Quite a bit because of the gas. Not so true with the solid to liquid transition. I'm not going to say it's completely independent of pressure, but enough where we're not going to be worrying about fusion curves being, dramatically curved like a vapor pressure curve. A fusion curve is mostly like a straight line, right? Relatively independent of pressure. We'll see that later when we look at phase changes. So again, the point where the temperature, where you have a solid and you've increased the vibrations and whatnot to the point where it starts disrupting some intermolecular forces and creates a little more mobility, and you have a liquid, that's the melting point. And the reverse of that, of course, right? You've got the liquid moving a little bit, you cool it down. What temperature does it lock in? That's your freezing point. Those are the same thing, right? Melting point. So I never see anybody use FP for freezing point, right? But you can say it, right? But it's the same thing as the melting point, same value. So for water, of course, ice, 0 degrees Celsius. Growing up in Minnesota, we knew, well, obviously most people think in Fahrenheit, degrees Fahrenheit. So 32 degrees Fahrenheit or 0 degrees Celsius. Woo! We can get some snow. It's kind of cool. I was just up in Big Bear with my kids, right? Sledding. It was really neat. So that's 0 regardless of which way. So if you have an ice cube, get it to 0, it should start melting. Right on? And if you have liquid water and you get it to 0, it starts freezing. Same thing. Now, if you compare the melting point of potassium iodide, that's 677 degrees Celsius. That's a little bit higher because it's an ionic compound. It has those super strong ion-ion forces. Way stronger intermolecular forces than the hydrogen bonding and London dispersion. Of course, they both have London dispersion forces, which are relatively non-important for the ionic compound and not super because this has hydrogen bonding. But you can see, you can understand why based on intermolecular force strength. Something that has stronger intermolecular forces is going to have a higher melting point. Same thing's true for molar heats of fusion. So if I want to do a phase change from a solid to a liquid and I want to completely melt it, the energy it takes to do that is the delta H sub FUS, the molar heat of fusion. Right on? I guess you could say molar heat of melting, but nobody says that, right? Of course, that is determined by the intermolecular force strength. So a solid with stronger intermolecular force strengths is going to have a higher molar heat of fusion. It's going to take more energy to convert exactly 1 mole of that solid to 1 mole of a liquid. Make sense? We'll also have a higher melting point. The reverse of that, if we're going from the liquid to the solid, that's freezing, of course. So that'd be the molar heat of freezing or molar heat of solidification. That is the exact same number, just like the melting and freezing point. So for example, for water, to melt ice into liquid water is 6.01 kilojoules per mole. Right? These are not exact numbers, by the way. Well, the molar heat of freezing should be exactly the same number, just opposite, because when you take a solid and melt it, it requires energy to disrupt those intermolecular forces. That's an endothermic process. That's why it's positive. And this is all on that video on heat. When you're freezing it, it's the opposite, right? You're reversing the process, solidifying it, and then there's an energy decrease. Boop. That's released. Okay, so that's exothermic in that process. So you get that if you study atmospheric chemistry or weather. So I read a whole book on meteorology once. So when you take, and this is a different phase change, but when you take the water in the gas phase and it condenses into a liquid or into like snow or something like that or sleet, there's an energy change that occurs, right? That's an exothermic process which releases energy, and that can cause interesting aspects of weather. It was kind of neat. I was like reading through it. I didn't know much about meteorology, but I'm like, I understand that, and that's why the wind formed there. And it's kind of interesting, right? Knowing chemistry just makes you smarter and more appreciative of life. All right. So quick review on heating and cooling curves. Let's take a look at those. A lot of review here, but it's all in that video on heat real quick. Let's do a quick little review of heating and cooling curves, which were, again, covered in great detail on that video from thermochemistry last semester. Let's take a look. This could be water, could be any substance, right? So let's say we've got something in the solid phase, right? So we're starting here. So let's make a little graph. We got the temperature, it doesn't have to be in degrees Celsius, and then the amount of energy applied. Let's say we take, like an ice cube, and stick it in a beaker, put it on a hot plate or over a Bunsen burner. Let's say it's over a hot plate, and we start jacking up the energy. And let's say that ice, right, is lower than 0 degrees Celsius. Okay, so this is in the solid phase. So say we have ice at negative 10 degrees Celsius or something. If we add heat, is it going to melt immediately? It's not, is it? We got to get it to 0 degrees Celsius, correct? So what's going to happen is as you add heat, you'll see the temperature increase, right? Until you get to the melting point. And then once you're at the melting point, so this would be your solid right here. That'd be your solid phase. And then once you get to the melting point, all the energy goes into disrupting those intermolecular forces. And so at that point, you've got an equilibrium between the solid plus the liquid. All solid here, you got a mixture, all liquid there, right? Remember that? And then once you've got the liquid and you're still adding heat, cranking up the hot plate, whatever, it doesn't boil immediately, does it? You start increasing all the motion until you get to this point here where it starts to boil. So this is the boiling point. Imagine that's a perfectly straight line. So this whole phase right here is just liquid. This is a heating curve, right? As you add heat, what happens as the temperatures, what's happening as is the temperature increasing? Is it staying constant at a phase change? You can tell where the phase change occurs. It's pretty easy where the temperature stops increasing, and you can visibly see it go from a solid to a liquid. You can measure that. You do that in organic chemistry labs a lot. You have that little melting tube, that melting point apparatus, and you just watch it through the microscope and you see it melt. Boom! You measure that temperature. Right? Now here at this point, you've got that equilibrium between the liquid plus the gas or vapor. And then once you it's all liquid here, all gas there, you could continue heating it. And if that was if that was water, that would be steam, right, in the gas phase there. And you can have steam at 100 degrees Celsius or steam at 200 degrees Celsius, right? That's called a heating curve. And if you remember from thermochemistry, you could do the calculations for this, right? So anytime you have the temperature change, this would be Q equals ms delta T, right? Call that, say, Q1, heating the solid. And then at the phase change, we would use Q, call that Q2, N delta H, fusion, righty-dighty. And then here we've got a temperature increase. Let's call that Q3. That would be ms delta T. Some people would go MC delta T, the MCAT, right? Depending if you call it specific heat or specific heat capacity. Up here at the boiling, right, this would be Q4, which would be N delta H vaporization. And then if you're heating up the gas, Q5 would be ms delta T. So you can calculate the amount of energy it takes at each of these, right? So that's a heating curve. Now for a cooling curve, we just start at the gas phase or whatever phase and start removing energy via loss of heat. Boom, and we're just going backwards. So you're reducing the temperature of the gas to the boiling point in this case, or condensation point, and then you're condensing it, and then you'd cool it down to the melting point or freezing point, and then you'd freeze it, and then you could keep cooling down the motions of the particles in that solid. Now, I do want to, I'm going to pause this for a second, clean this up a little bit. There's something really interesting that can happen at this point where when you're cooling it, it doesn't quite freeze at what you would, if you know the freezing point, you can see it actually keep dropping in temperature. And so you're below the freezing point, it's still a liquid. You're like, what? Let's talk about that weird thing. Doesn't happen a lot, but let's talk about it just in case you ever run into it. All right, you ready for something that you may or may not run into in your whole life? I don't know, but let's flip it. The other one we did was a heating curve. Let's look at a cooling curve. We'll start up here with the gas, right? And then we'll cool it, cool it, cool it, cool it. It condenses from a gas to a liquid. Cool it, cool it, cool it, cool it, cool it. Freezes to a solid. You can keep cooling it, cooling it, cooling it, right? So you're just going backwards, right? Sometimes you see graphs, instead of plotting heat energy here, they'll plot time. And so with the cooling curve, they'll flip it and start here and go like this over time. It doesn't matter, right? But you may see this. Are you ready? You condense it. You're cooling the liquid down. You expect it, if you know the freezing point, you expect it to freeze, but you'll see that it stays as a liquid and drops. And you're like, what is going on? And then you get this little curve that pops back up. See that little dip? So what happens is it freezes. It's still a liquid below the freezing point, and then all of a sudden it pops back up to the freezing point and then is isothermal from that point on. That is a process called supercooling. Oh, super cooling. And that is where you can have a liquid exist as a liquid below the freezing point. It's very weird. So the liquid briefly exists at temperature values less or lower than the freezing point. Well, how does that happen? Why would you get that? Well, there's a lab we do, or we're going to do, where we're going to make these beautiful green crystals. And we let them, so we mix the stuff up and let it sit, and we'll cover it up to keep dust and stuff from getting in there and let it sit for like a week. And if you do it just right, if you cover it up well and it doesn't have impurities in there, you end up getting like one gigantic, beautiful crystal. So gorgeous. If you don't do it right, and maybe you get a lot of dust and stuff gets in there, you might get 50, 60, or 100 smaller crystals in there, right? Which isn't quite as pretty. It still works, but it's not quite as pretty. Well, what's happening there? Well, if you have those little dust particles in there, the ions start to glom onto those. It's called a nucleation point, and that's where solids start to grow. So if you have lots of dust particles in there, you can get lots of nucleation points or centers where solids start to form. But if it's really clean, you don't have particles in there and whatnot, you can get one, if you just have like one little dust particle, you can get this one gigantic crystal. It starts at that nucleation point and then grows, and everything jumps on board. Hey, everybody jump on board, right? It's kind of like, I guess like if they're seeding to make rain, they can fly in there. What is it? I can't remember. Was it silver iodide crystals? I can't remember what they shot into the clouds. But the water molecule, the vapors, would glom onto those little particles, and then more water would glom on until it got heavy enough and it would rain out. You could seed it. Okay? Supercooling is a similar thing. As it's cooling, right? So for those liquid molecules, right, to freeze out, they glom onto centers. So if there's dust particles in there, it will start freezing right off the dot, right? But if it doesn't, it might drop a little bit and then latch in and get into place, right? So it's dependent on condensation nuclei. I'll write that in there. So it depends. Whoops, if I could spell right, that would work better. Depends on the presence of condensation. Getting a little squishy here. And again, not critical. We're going to run into this in the lab. We're not going to study this. Unlikely I have limited time on exams and quizzes, so unlikely I'm going to ask you stuff about supercooling. I just want you to be able to do heating and cooling curves, and Q equals N delta H and whatnot. Expect in the homework some practice problems from thermochemistry last semester. Q equals N delta H, MS delta T. So if you don't have many condensation nuclei, you might see supercooling occur, right? But if you've got particles or areas where they can latch onto, you'll probably just jump right into the normal isothermal line there. Okay, so that's for supercooling. That's enough for melting and molar heats of fusion. Let's take a look at sublimation. Not as common, but since sublimation is a solid to a gas, we get some interesting parallels with liquid to gas. Let's look at that. All right, we covered melting. Let's look at sublimation, which you won't run into nearly as often in your whole entire lifespan. Some of you might go through your whole life and not really run into this at all, but you've probably seen it. You've probably seen it. So sublimation, of course, is going from a solid directly to a gas. You're bypassing the liquid phase. We're going to find out this is highly pressure dependent. Okay, so we're just reviewing introductory chemistry right now. So I'm assuming you mostly know sublimation. And the reverse of that, of course, is deposition, going from a gas to a solid directly. Paralleling melting, right? The energy required if we have exactly 1 mole of a solid and to convert it to 1 mole of a gas, that is the molar heat of sublimation, just like the molar heat of vaporization, delta H vap, molar heat of fusion, delta H FUS. We got delta H sub. It turns out this is really nice because technically you're going from solid to gas, which is solid to liquid and then liquid to gas. If you know the delta H fusion, molar heat of fusion, and molar heat of vaporization, you just add those together to get the molar heat of sublimation. But we can solve for this using we're going to find out we can use the Clausius-Clapeyron equation just like we did for boiling. And I'm going to show you, I'm going to drive that for you, show you that equation where we could actually calculate that experimentally if we wanted to. Hey! But not as many solids, because we mostly do everything at roughly atmospheric pressure, sea level, roughly room temperature. So we've got very constrained pressures and temperatures in our laboratory environment. So the majority of solids aren't going to sublime under those conditions of pressure and temperature, right? So we just don't think about it as much. All right, of course, the temperature, when something melts, is the melting point. When something boils, it's the boiling point. Of course, when it sublimes, it's the sublimation point. But you don't hear that term hardly ever. Right? We hardly ever run into it. We're going to find out that just like the boiling point, because there's a gas involved, whether you're going liquid to gas or solid to gas, because there's a gas involved, it's highly dependent on pressure. So we're going to, on the next board, we're going to draw sublimation curves, which look very similar to vapor pressure curves. And you can have a pressure, right, of a gas above a solid. We looked at the pressure of a gas above a liquid, the vapor pressure. We could also have the vapor pressure above a solid, right? So examples you may have run into, most likely if you've ever watched like fun chemistry videos or magic shows. I do that for Science Night a lot, little magic shows. So one of the first demos we like to set up when people walk in is we'll have these chunks of dry ice, which is solid carbon dioxide, really cold, right? Don't be dumb like me and hold it in your bare hand. That really causes wounds. Okay, so always have gloves. But you can leave it out and you can just see it go from a solid to a gas, right? And it creates these really cool little magic shows, right? That creepy little vapor that goes around. Another fun thing is when it's subliming, it forms a little layer of gas underneath it. So it's like you ever play air hockey? So if you take a chunk of carbon dioxide on a flat counter, you can slide it and there's hardly any friction because of this little layer of gas from the sublimation below it. So it's like it levitates. It goes woo, woo, fing, and it's kind of fun. But don't touch it with your bare hands. Trust me on that one. I had the blisters to show it. All right. So let's take a look at sublimation curves, those kinds of things, and how this parallels a lot the liquid to gas or the boiling point process. So this will be a deja vu for you. We did the exact same thing when we looked at liquids converting to a gas. We're going to do the same thing. So let's say we have, if we had an open container, the solid could sublime and then the gas particles would just dissipate in the atmosphere. Kind of like when I grew up in Minnesota. Ice, not dry ice. Dry ice is solid carbon dioxide. Ice is just solid water. It sublimes a little bit because in Minnesota it'd be cold. I mean, the winters are really, I'm Southern California right now, but they don't know what cold is. But it would snow and it would, obviously you might have a day or two where it stops snowing, but the snow stays there. But you could watch from day to day, and you would noticeably see the level of the snow had gone from, it was like 2 feet down to like, 1.5 feet. Not that I sat there and measured it, but it would pile up pretty high sometimes. If you let it snow for quite a few days, especially if the snowplows hit it and pile it up, I'd be walking down the street to school and be over my head on the sides of some of the streets. It's just nuts. But the snow would start going away, but if it wasn't warm enough to melt, it wasn't melting, right? But it was still disappearing, which means I didn't know when I was a kid, but now I know that even the ice was subliming a little bit, okay? Going directly to a gas and dissipating. Iodine's the same. Iodine's one of my favorites. It's a really cool kind of a dark grayish black solid, and literally right around room temperature or a little hotter, it will sublime into this beautiful, purple's my favorite color, into this beautiful purple gas. You don't want that dissipating into the atmosphere, like into your nose, right? So keep that in a closed container. And if you put some ice up at the top, you get the crystals reformed. It's under deposition. And so you get the solid here and you get the purple vapor, and then you get these little silvery gray crystals like a crystalline palace. It's really neat. But let's say we have a closed container, so the gas particles can't dissipate. We'll form an equilibrium like we did with the liquid and the gas. So if we have the solid, let's say it's subliming, right? And you're getting them into the gas phase up here, but it's a closed container, so they can bonk and go back into the solid, right? So you can get deposition, so you can get the same situation going. So the red would be the sublimation, the green would be deposition, but we could form an equilibrium, right? So at equilibrium, where we've got the solid converting into a gas, but coming back into the solid at the same rates, two opposing processes occurring at the same rate, dynamic equilibrium. So at equilibrium, the pressure of the gas particles. Now for a liquid, we call that the vapor pressure, right? So this we call the sublimation pressure. It's the same idea, right? It's a vapor, right? It's the gas, but we, commonly we use a sublimation pressure to note that it came from a solid rather than a liquid. Well, would it make sense if you increase the temperature? You're going to get more, you're going to break more intermolecular forces, go into the gas phase, and so that's highly temperature dependent, and we could draw a sublimation curve, which looks just like a vapor pressure curve. Let's draw that, right? Pretty fun. This is what happens when you have like iodine, and then if you put like a little bowl of ice up here, you get the little crystals that deposit up there. It's so cool. You should be able to draw this without my help, right? So if you remember the vapor pressure curve, let's do the same thing, but with sublimation. So let's make a little graph. So we can measure it in lab and get a data table, right? So we could make a data table of pressures, but instead of vapor pressures, we call it sublimation pressure. As the temperature goes up, the pressure of the gas above the solid increases, and we can plot that, right? So let's put the pressure here, and that could be atmospheres, millimeters, mercury, whatever. Let's put the temperature here. We're chemists. We're going to do that in degrees Celsius, right? And you will see the same, it looks exactly like a vapor pressure curve. Whoop! Curves up like that. And then if you're at sea level, right? Well, this would be the sublimation point, any point along this line. So if you're at some temperature, right? You could go up, boop, 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 hit that sublimation curve, go over, and find out what that sublimation pressure would be. That would be called the if you're on that curve, that's the equilibrium between the pressure, between the solid and the gas. So that'd be the sublimation point, kind of like the boiling point for a liquid and a gas. If we are at 1 atmosphere, can't seem to draw, that's the equilibrium between the gas and the solid at 1 atmosphere. Now remember what that was called with vapor. With a liquid, that was called the normal boiling point. Well, you would call this the normal sublimation point. Or sublimation temperature. So at 1 atmosphere, sea level defined, we would call that the normal sublimation point. But you can see as the pressure changes, as you decrease the pressure, it changes the sublimation point, just like on a vapor pressure curve. And if we wanted to plot that like we did the Clausius-Clapeyron equation, if we want to make that into a straight line, oops, I spelled it wrong. So if we want to get that into a straight line so we can do a least squares fit, get the y equals mx plus b, same thing, you dork around with the variables, wah, wah, and do the log of the sublimation pressure versus the inverse temperature. And that would have to be in Kelvin, so you'd have to convert the Celsius to Kelvin and do that. And then you get that negative sloped line. Do your least squares fit, and you get your equation for that straight line. Now remember how we derived the Clausius-Clapeyron equation? I'm not going to do it again, but on the next board, I'm going to write the Clausius-Clapeyron equation again. But it looks exactly the same other than the slope. In the Clausius-Clapeyron equation, that was based on the molar heat of vaporization over R, the gas constant. In this case, what determines the energy to sublime something? The molar heat of sublimation. Ho, ho, ho! Yes. Exact parallels. Let's do it. Let's draw the Clausius-Clapeyron equation, the clap. Let's draw the clap and just reinsert delta H sublimation for delta H vaporization. You can do the exact same thing. And in the next video, we're going to put all of these processes together into one fell swoop called a phase diagram. That should look mightily familiar. And again, we're going to see this same type of equation pop up, I think, 4 times this semester. Clausius-Clapeyron equation for vaporization, when we put VAP there, that was for the liquid to gas. We can do the same thing for sublimation. It's exactly the same, right? So P2, when you took that equation, separated, subtracted at 2 different points, you get the ln P2 minus ln P1, which is the same as P2 over P1. We factored out delta H sub over R negative. You get 1 over T2 minus 1 over T1. So I could give you 2 different temperatures and 1 pressure and say, well, what would be the sublimation pressure at some other temperature? Or I could say, hey, if I give you the 2 pressures, I can say, what's the sublimation point at some particular external atmospheric pressure, right? Or barometric pressure. And we're going to see this again in kinetics, I believe. We're going to see it in kinetics later on down the road. In one other point, I can't remember off the top of my head, but we'll see, like, say, an activation energy term in there. And what, it's bugging me, I can't remember that. Dark, but you'll recognize it when it pops up. So again, exactly the same. I'm not going to do an example for this. Look at my Clausius-Clapeyron equation example using delta H vaporization. Exact same process. Okay. Let's do phase diagrams in the next video. We put it all together now.